No? All right. Yeah. So I'm going to talk a little bit about Jupyter. The name of the talk is State of Matters. I didn't pick the name. My boss did. He couldn't make it today. And when I started preparing the talk, I was asking myself, does the title reflect what I'm going to say? It's about to, what the idea is to tell a little bit what is the status of the project. And I started thinking, is the state of matters correct, like grammatically correct? And I got a little bit sidetracked. So I Googled it, if this is really a thing. And of course, all the answers were state of matter, not matters, right? So that gave me a good start into the talk. Because then I could think, is the project in a solid state? Is it fluid? Is it gas? And I think now it's more like lining. It's more like plasma. All right. So what I mean like that is that it is in a very hot phase. It has rapid changes. It's difficult to predict what's going to happen next. Kind of want to touch it, like these plasma lamps that you see and you really want to put your finger on there. And plasma, like the project, can also kill me. So an alternative way of looking at it is looking at Jupyter as the planet. So and that way it's similar. It has a solid core. The project has a solid core. Planet as well, I hope. I'm not a astronomist. It has kind of nebulous surroundings, difficult to reach. It's kind of mesmerizing, and it can also kill me. So with that, I guess we can start on what is the project about. So we can take a look at the distant past. I don't know who here already had or heard something about Jupyter or was in a talk about Jupyter in the past. Raise your hand. Like 50%. Okay, it's gonna be boring for you. I'm sorry. I hope for everyone else it's a little bit less boring. Yeah, so the distant past. So it all started on Jülich becoming a hosting site. So on EuroHPC, all the systems that are coming from EuroHPC, they start like a site, present their proposal to become a hosting site, and well, as it says, hosting a system. And that started in December 2021. That is forever ago. Well, there was the call for expression of interest, and then Julie said, well, we would be interested. That was the call from EuroHPC. There was a deadline for application in 2022 on Valentine's Day, perfect day for the deadline. And well, so there was a series of things on the application. So we present our candidacy, and we said Jülich would like to host in Europe. Right. So there were the first set of hearings, a little bit, about 3 months after that, and a decision taken roughly 3 years ago. Almost, not quite there yet, but a long time ago. Right. So well, turns out that our proposal was successful. EuroHPC liked it. And we got selected to host Jupyter, which at that moment was not called Jupyter, I think. Right, well, we come up with the name about that time, let me put it that way. Good. So what happened after that? Then we needed to start laying the foundations for the project. So we had the decision from EuroHPC, and well, we started to start thinking on how we are going to actually do that. There were, of course, some there were ideas, but we had to concretize them, so to say. And after, well, a series of meetings, discussions, iteration of the proposal, explaining how we intended to do it and what we actually intended to do, then we came to the hosting agreement that was signed, and well, everyone was happy. So that was the base, so to say, for launching the project. So yeah, at this point, our target is Jupiter. We're still on Earth, and we need to go through all the preparational steps. There's one important aspect on the project, or well, on Jupiter as a system, and is that this is not a single project. This is an aggregation of at least 4 different procurements that had to align to come to the point where we are now, and we'll come to that later. But basically, we had the procurement of Jupiter itself. We had to align that with the procurement of storage, because the storage, or most of the storage, we'll see later, there's 2 different tiers, but one of the tiers is not part of this procurement. So there was an in-kind contribution from Ulysses to align that with Jupiter, and we had to align the hosting infrastructure for it as well. You've been here 3 days. You see that Jupiter is not on those windows over there. It's in a different building. Guys got to walk around. There's a tour afterwards. But basically, well, the current data center is not big enough for it. So yeah, so we had to figure out a way of building a new data center in time for hosting the system. That's again a separate procurement that had to align with everything else. All right, so that's where we are. We started with on Earth, as I said, and there's well, we're ready for takeoff. We had this slide before with a rocket from SpaceX. Wanted to change it now. This is an Ariane rocket for reason. So we were, yeah, basically ready for takeoff. So there was an overall budget for the acquisition of almost 300 million, 273. It was a high-level description of what we wanted, and well, that's more or less it. So at that point, there was an invitation to tender. That's a call for the vendors to say, well, we'd like to have a system. What do you offer? So we published a call in January 2023. That's yeah, more than 2 years ago. So you see, time is passing by. And well, about 1 month later, there was the deadline for participation. So any vendor that wanted to participate, they could raise their hand and say, well, we would like to be part of this. This is more or less how our proposal will look like. Yeah, so let's keep talking. So there was a period of evaluation of these, let's say, pre-proposals. And well, there were basically 2 proposals from 2 different consortiums, one from HPE, one from Patek. Yeah, full day in Luxembourg, everything very secretive. There was no communication of the proposals, no emails or anything like that. It was on paper, so people needed to go there and take a look at the physical copies, very 21st century. Well, basically both of them kind of made a cut for the first stage. The way this procurement worked, I think, I'm not completely sure, but I think all the procurements from your HPC, they are competitive dialogues. What that means is that the companies that have been interested in it, we get to talk to them in a series of talks, not simultaneously, so one day after the other. So first one company, the next day a different company, to kind of iterate over what is our vision and what is their vision, and align more or less targets to make sure that what we get is the best we can get, and at the same time that the effort they put is also aligned with so to say, with their targets. So we had the first dialogue, then we had a second dialogue, and then the final invitation to tender, with a deadline again 1 month after the final invitation. Here I have to say that the vendors did, in my opinion, a fairly good job. We requested a lot from them, and we didn't give them a lot of time. So that's something to consider. Sometimes we are a little bit tough to vendors, but you have to admit that we didn't make it easy for them either. All right, so there was another evaluation, and well, similar to the previous one. One thing that is important is that during this whole process, we wanted to put a lot of emphasis on real performance, not just on technical specifications or exaflop or anything like that. That is, of course, the biggest goal or the biggest political goal, but it couldn't be just a machine just for saying we have one exaflop and then real performance, we don't care. So we put a lot of emphasis on that. And during the during this whole process, we had we developed what we call the benchmark. I forgot how we call it exactly, but basically a set of benchmarks and a platform where these benchmarks need to be run, and vendors will need to make commitments based on that. So that involves the whole institute, or not the whole institute, but a big chunk of it. And well, apparently that's something that went overboard, but at least it looks like we exceeded the expectations. Right, so that was a relatively stressful period. I think not as stressful as what is coming after that. Right, so then there was the meetings to decide, well, and to evaluate what the proposals from the vendors actually said, and and at that point there was the decision was taken, and the vendors were notified. And there, well, you see that there's already this one small obstacle on the route to Jupiter. At this point, one of the vendors that won decided to announce it before anybody else, and then everything kind of froze for 2 weeks until everything was made clear. Okay, we are safe, because we are supposed to wait a little bit in case the other vendor wants to complain or wants to mention something else. Anyway, so luckily we survived that obstacle. We could kind of avoid a collision, and the contract negotiations started, and everything was signed in October 2020. Right, so at that point, all the press releases came out from everyone, not just from one vendor, and well, then we started things in motion in a more, let's say, concrete way. Right, so as I was saying before, we put a lot of emphasis on applications during this phase. So what we basically did was we took a look at what people are running on our current flagship system on US Booster. That's what you can actually see through the window here. And we try to have something that is representative of those actual workloads as a basis for benchmarking the quality of the proposal. Right, so that's more or less what I mentioned. We went through the effort of making things easy to benchmark. I think, well, we talked about it a couple of times during the last 3 days. Scientific code is not always that easy to use or to reproduce, or it's not that straightforward. So making sure that things are smooth and can be run in a way that is fair for everyone involved, and that actually gets you the metrics that you need and stuff like that. That is not an easy thing, and especially to make it homogeneous across different communities and different applications, that is a small challenge on itself. But we kind of went through that journey. So we took a look at the projects running on our flagship systems, and we kind of benchmarkized them, so to say. So those, what you can see there is a pre-selection. Most of them made it into the final cut, so to say. there's, well, a number of criteria for selecting or for thinking if we can put those codes into the evaluation or not. We're also trying to balance things like programming models, scientific domains, how available were the people behind, or how responsive they were, willing to adapt to changes, stuff like that. And well, and we also had a couple of other benchmarks had between, not just from applications, but also synthetic benchmarks that would give you a little bit of more, let's say, close to hardware idea of what some of the metrics could reach. Right. So with that, we kind of iterated over some months, and we went through that process of reviewing what we have, selecting the codes or the applications, prepare them, meaning that, well, we needed a set of documents describing what this is about, what is the input, what is the expected output, what is the performance we get on the current system we have, things like that, and then kind of iterate over that and then publish it in a suite. We divided things a little bit further, taking into account not just if they are real codes or synthetic, but also what were the targets. Not all the codes that were included there were GPU focused. Most of them were, but not all of them. So we needed to include that. We wanted also to make some space for MSA, for this modular supercomputer architecture. So basically making sure, well, having something that can run simultaneously on a partition without GPUs, on a partition with GPUs, and stuff like that. And we also divided benchmarks on two separate categories, what we call TCO and the high scaling. The high scaling was something that was kind of new for us, and basically taking those codes that had higher chance of scaling to exaflop. And the fact that you are going to run an exaflop system doesn't mean that you're going to use the full system, that you're going to scale to that. But that is, of course, the kind of grand challenges that are more interesting for us. So we also needed or wanted to put some emphasis on that. Right. So we ended up more or less with this selection, and most of it, or the bulk of it, was on the TCO part of the equation, so to say. That is the TCO. That's also, yeah, a little bit of a more traditional kind of benchmark. So not looking at the high scaling, as I was saying before. And what we try to measure is how much science we could get per piece of the system, so to say. Well, it was a relatively complicated formula to try to combine or take into account all the different aspects of it, and well, and that was more or less it. Right, for the high scaling, well, a little bit what I mentioned before. Those, we made a small selection to see which codes of all those codes, a small selection of the ones that could scale, with a little bit of the idea that the Jupyter is supposed to be about 20 times bigger than what we have now. So we tried to see how that code, or what would be a sensible experiment for those codes in a system that is 20 times as big. Right, so there's lots of small details about that. At the end, well, there were some that fall down from the pre-selection, and well, all of that was all committed to a website that the vendors had access to and that they used for the let's say for their commitments. All that at the end ended up in being a paper that was published in Supercomputing last year. So if anybody's interested on all the details that I probably can't explain or that I forgot, you can probably take a look at the paper. All right, so what was the result of it? The result was then Jupyter, and how is Jupyter looking like then? The main core of Jupyter will be the what we call the Jupyter Booster. That's the GPU part of the system that it's contractually going to reach 1 exaflop on its own. I put emphasis here on contractually because that is something that is written, and so if the amount of hardware that is going to be supplied does not reach it, we're going to get more hardware. Right, there's another part of the system for codes that that might not be able to use GPUs. We have still a relatively large community of applications and users that that are not able to use GPUs, and we kind of need to take the integration as well. So there's a smaller part of the system that would come later. But I would say that at the moment, 90% of what Jupyter means is more the boosted part of the system. And that is going to be deployed on a modular data center. What is meant by modular data center is a data center based on, I don't want to say containers, but prefabricated modules. They are not standard containers like you see on ships going or bringing goods from one place to another, but they are prefabricated and they are assembled somewhere else and then brought up here. If somebody was here on Monday, maybe you saw some of them actually, because we got a couple of them coming on Monday. On Tuesday they were all delivered already. Good. So that is kind of the rough structure of the project. Right. So well, this is more or less what I was mentioning, but a little bit extended also with other modules and part of the system, so to say. There's starting on the upper right corner. There's the tape that is already actually deployed. The tape is not going to be on the modular data center, the tape library. That is something you can see already through the window. We had the same technology already deployed for a number of years. There's an extension now. So if you look through the window down to the right part is what is new. Then we have the parallel file system based on spinning disks, when you see right close to the tape. Right. Those two parts are not part of the procurement of the project, of the project. Well, understanding that as part of the procurement with Euro HPC. The parts that are part of the procurement is what you see more or less surrounded in red on these boxes. So well, now if you keep moving, then you see the flash-based storage cluster, and then you have what I mentioned already, the GPU cluster and the CPU universal cluster. There's a space for a number of other modules. The fabric has a space to grow, not to the same scale as we have now, or we're going to have now, but there's space to grow for integrating future modules, like what Madita was mentioning before, and there's possibilities to integrate quantum computers or other kind of technologies to be evaluated as part of the same system. Going into more detail on the compute part, is it until now, is it boring? Is there something else you would like to? Should I spend more time on something? Until now it was very political, I think, and very project management kind of thingy. The technical details come now, so I hope that becomes more interesting.
Maybe someone has a question already?
If somebody has a question, please raise your hand. I mean, otherwise it's boring and it's 1 hour talking, my throat gets dry, so don't be shy.
And I actually have a question. If you can go back one slide. Yeah, so you mentioned essentially the storage part was not part of the procurement.
Right.
So you're buying a supercomputer without storage.
Yes and no. There is 2 tiers, meaning 2 separate storage clusters. The flash-based, that is part of that procurement. The spinning disk-based is not part of the procurement, meaning that Julius set aside some money that had nothing to do with this procurement. Well, I should stop saying procurement so loosely. With this
project.
With the project with EuroHPC, so we set aside some millions to have an in-kind contribution to the project. What that means as well is that money that otherwise would be allocated for storage can be allocated for more compute nodes. Does that make sense?
Yep.
That of course becomes a little bit of a orchestrating nightmare, because then you don't have to talk with one vendor, you have to talk with 2, and it's actually not 2, we are talking almost with every vendor, because there's a lot of people and a lot of different companies that are involved, and lots of subcontracts and stuff like that. So it's an orchestrating challenge.
So Jupyter itself is evident. What's the spinning disk part? Is that also evident or someone else?
It's somebody else. That will come later.
Okay.
It's IBM. And with some sprinkle of Megware. So we have a lot of companies working together on this journey. Any other question? Alex, you work here.
An internal question. Okay. It's getting interesting.
I'm missing one of those hexagons of the AI, the Jarvis thing.
Oh, well, yeah. This is a relatively... Okay, no, this is a small spoiler. There is what is called the AI factories, and that's being, I'm not super involved in that, so maybe I say something wrong, but as I understand it, after a series of negotiations, also with EuroHPC, there's a series of AI factories that have been approved for funding in Europe. I think there's 6 of them. One of them is going to be here. What that means, or as part of that project, is that set of compute power that it's going to have a different user base is going to be integrated into not into the fabric, but into the ecosystem of Jupyter. And as far as I understand it as well, will be deployed on the same modular data center. I don't know all the details because, as I said, until now I was not very involved in that, but that's more or less it. And we name it also starting with J, because everything has to start with J for some reason. We already have another cluster that is called Jarvis here, so that's going to be interesting for us. But it's an internal cluster, so that's okay.
Let's take that question. We also have to be mindful of time. We're about halfway in the hour now, so, but yeah.
Just quick question about, because this is all hardware, I'm curious how much of the tooling was included in the procurement, like all the monitoring, logging, Slurm?
We'll come to that.
Okay.
We'll come to that. That comes later. All right. Then, any other question? Okay. Then I'll just go ahead. So yeah, I'm gonna focus now mostly on the booster part. That is the part that is more pressing right now. This is how it looks like. So it's gonna have 125 Sequana racks. I don't know if people are familiar with the Sequana architecture. Anybody knows what Sequana is? Couple of hands. Okay. Sequana is basically the architecture for HPC and now AI, because everything has to have AI on it, from EUM'25. They are very, very dense. They are directly liquid cooled, and well, that's basically what you get for custom big iron HPC systems from EUM'25. What we have, again, I'm referring to what we have through the window. There you can see the two previous generations of Sequana. So here's Exascale 3000. We have the 2000. We have the 1000 on the current data center. They look very similar. The 2000 and the 1000, they look very similar. The 3000 is a completely different beast. They changed a lot of things. They improved lots of things. So yeah, we're relatively hopeful. We actually have one rack of this platform that will come later, so that's a small spoiler. but we have one rack for almost 1 year here, and it's been quite solid. Right. So we're gonna have about 125 of those racks. Just to have it mentioned now, in connection to the MDC, that means that we're gonna have about 20 of those racks per room. We're gonna have 7 rooms. The last room will have just 5 racks. Just as a well, keep it in mind because that connects as well to the model that you can see also outside of the window. Of the room close to the window. All right. Each one of these racks has 48 nodes, which are divided in 24 blades. Each one of these blades with 4 CG1s, so 4 gracehoppers, meaning it's a little bit special in a way, in the sense that we have a ratio of 1-to-1 from CPU to GPU. That's a change from what we have now, and a change from lots of other different systems. There's a lot of CPU power that I'm not sure it's going to be very well used to its full extent, since you should put the focus on GPUs on the system. Right, so there are some specs. You can read them. That's probably not that interesting. There's another part of the system, the part based on the part without GPUs, just with CPUs. This part of the system is going to have. It's going to be based on the processor from Cypel. But that will come a little bit later. So at the moment, as I said, 90% or more than 90% of the focus is on this. All right. Everything else on this slide is just specs. I wouldn't say they are boring, but everyone can just read them online. Well, this I already mentioned a couple of these things before. One thing that is interesting is when you see the relation of GPUs and injection bandwidth. On this system, we're going to have 4 HCAs per node. That is the same that we have now. It's a ratio of 1-to-1. What is interesting, or one thing to notice, is that it's NDR, it's InfiniBand NDR 200. 200 meaning 200 gigabits per second. That is the same bandwidth we have available on GBoost Booster on the previous generation. On this kind of systems, the price of the network is a very, very big part of the overall price. It could be possible to make it with NDR 400. It would be just way more expensive. Or you could have it for the same price. You can have NDR 400, but then you will have way less compute power. So trade-offs. Right. Yeah. Everything else I think I mentioned it before. This is a picture of the blade. I think I have it in bigger later. I think I have it bigger later, so we'll take a look at that later. Then, as part of the system, well, we talked a couple of times about that already. We're gonna have a storage. This is the flash-based part of the system. We're gonna have 20 of these EESSI 6000 building blocks from IBM. We are a kind of a GPFS house. We have the expertise for spectrum scale now, and we wanted to kind of have some continuity. Not everything needs to be a hard challenge. And on this part of the system, or of the storage, basically each building block has its own disks without extra set of JBots. That's a difference with the next one. The next one, it looks very similar. It's the same kind of servers, but they are not flash based. They are spinning disks, and we have Each one of these building blocks has how many are there? I think 7 of these JBOD arrays. One thing that is for people that have access to our systems, one thing that is important to notice here is that both of these storage clusters are exclusive for Jupyter. The storage clusters we have now, they are shared across all our systems, and that has implications on the overall architecture. In this case, positive implications. Both storage clusters are integrated in the InfiniBand fabric, which we hope is gonna give us a little bit more reliability. It also allows us to do RDMA directly to storage, which we couldn't do before because our systems have InfiniBand, but the storage has Ethernet. We had to bridge that gap. If you bridge that gap, then you lose RDMA. So that's not the case anymore. We can also do things like GDS. I don't know if people heard about GDS, this GPU direct storage, where you basically can write directly from GPU buffers directly into storage. That's gonna be supported here. I mentioned before, so IBM, this part of the system, IBM is the subcontractor, but everything is the first contact point for us. For Exaflash, here is IBM together with Megware, Megware for some of the supporting and admin nodes for this part of the infrastructure, under Rax, if I'm not mistaken. All right. Any question until now before I jump into node design? Yes, 2 questions.
What's the question?
With a cluster of that size, do you do some kind of pre-data fetch? So the data is local to compute, and then you've got a pool where all the nodes can access it, and then you push it back, or do you just access your storage directly?
Means some sort of bus buffer?
Yeah, something like that.
No, we had a system before that had a bus buffer. That was interposed in the GPFS layer with everything else. That didn't work that well, but and that's the reason why we kind of changed the one of the reasons why we kind of changed the approach here. We don't have that bus buffer, but we have a flash-based storage. So at the end, if you are expecting to have that kind of requirement, then you can put your data in there or write your data in there. It's flash-based. I don't think it's going to be faster than that. Even a bus buffer wouldn't. I don't think that would be faster. Now with a kind of bus buffer architecture, then that can takes away the complexity of the user from moving data back and forth. There's a set of what we call data moving nodes, where users could, it's not going to be there on day 1, hopefully on day 2, where they could using API to talk with them and move data back and forth from the different tiers on the storage without having the users having to actively take care of that.
I tell you, the reason I'm asking is because we've got users who are running away jobs, and they've managed to get zillions of small files hammering our file system and basically bringing down our spectrum scale, GPFS, whatever you want to call it. And so we are, in comparison, a very small shop. So if you've got 3, 4, or 5 of these users, how does your file system?
We try to educate the users to don't use small files as good as we can. It doesn't always work. So at the end, it's one of the things. We also have a few courses, and one is Introduction to Supercomputing, and there's multiple talks there, and one of the talks based on I/O is, please don't do that. Don't use the small files, avoid it as much as you can. Yeah, So
Users who do the wrong thing on a current parallel file system will do the wrong thing whatever other system you try to use also. As soon as they need to do something manually to get it working properly or to inform the storage what needs to be transferred to your buffer system, they will not do it because they make errors basically because they don't accept that they need training.
yeah, that's been also my experience. Being said that, and also connecting to the fact to a spectrum scale going down on your side, I think the Achilles heel for this system, and I think for any system of these characteristics, to the network and the file system, and I just don't see any way around it. These two things need to work, but they are very, very delicate to make them work reliably at this scale. Do what we can to make them work as good as possible, but it's just the nature of it, so to say. You have a chain, and that those two things are the weakest chain when you need to take into account that these things need to work in parallel in a coherent fashion. Sometimes people come like, yeah, but clouds, they have more nodes. But yes, but they don't have a common vision across 10,000 nodes.
Damian, you told us that the spinning storage was contributed from JSC and that it is also exclusive to Jupyter, right?
Yes.
Okay, so there does not need to be a connection to the rest of the cluster integrated into the InfiniBand, right?
Does or it doesn't?
No, it doesn't. You don't need any connection to the rest of the cluster.
I'm not sure I understand the question. You
Okay,
need to integrate it into the InfiniBand fabric, because otherwise how you're going to access
Yes, for sure, for Jupyter, but not
Yes.
for the rest of the cluster.
Oh yeah, what do you mean for other systems?
Yeah.
Yeah, no, yeah.
Okay.
The other systems won't have access to it.
Then did you think about Omnipath CN5000?
Omnipath. Think on which sense?
Instead of InfiniBand, because it's much cheaper. You had more compute nodes.
Yeah, I mean, on one hand, it's not our, well, I mean, we could steer it. If we wanted Omnipath, we could steer it. But I'm not sure how Omnipath is connected. Maybe I'm missing the point, but how is Omnipath connected to the storage question and the fact that it's a different procurement?
Then the whole fabric question.
Okay, all right. Yeah, so it's a good question. We had two vendors that participated. One was InfiniBand based, the other one was Slingshot based. There's not that much we could steer there. We could influence, but they don't have the products to integrate into their architectures for Omnipath. On the Evident racks, the Sequana racks, the InfiniBand switches are kind of custom made. I mean, the ASICs are obviously from NVIDIA, but all the components around they are kind of they are custom made. The cooling plates they are directly liquid cooled, so you need to have some, or they did some development to integrate that efficiently. To do the same for Omnipath, that is a completely separate line of development. And Omnipath, we did have Omnipath here before. The experience was not great. I think now is better, but it's just what I think. I don't know it for sure, because we didn't have anything in-house, so to say, to play with it. Now, at the same time, the roadmap for Omnipath got stuck for quite a few years. So now they are moving into 400, if I'm not mistaken, but they've been on 100 for quite a bit. So that adds a little bit of a question of how reliable is this? A different question is also that you need to integrate that into the broader ecosystem. It's a little bit of, I don't want to say vendor locking, but you know that InfiniBand is going to work better with NVIDIA GPUs that Omnipath probably could. At the end, it's just an addition of multiple factors.
Okay, thank you.
We have about 15 minutes left.
Oh,
So, yeah.
all right. No questions anymore.
And then there's another part coming as well. There's a software part as well. So.
Okay. Yeah. All right. So I'm gonna just quickly go through the node architecture. That's it. This is the blade. We saw it already. Those are 2 nodes. I don't know if people were on supercomputing last year on the conference. Yes, hands up. Somebody saw this blade. We had this blade in this blade. It's heavy. It's big. It's not ugly. I think it's a nice blade. But yeah, but you basically see on the left 4 grasshoppers, on the right another 4 grasshoppers. Those are 2 separate nodes. You see on the front the HCAs and the ports on this case they are a standard OSFP. That's the difference also with the previous architecture where everything was going through a backplane. Here everything is a little bit more how can I say, less custom, which hopefully means more reliable. Right. This is how internally kind of block diagram, how it looks like. Thanks to Andreas for this. He's our master of graphics. You see the blue parts are the grays part of the system, or meaning those are the CPUs. The green part are the GPUs. You see the memories in between. You see all the buses connecting everything with everything. And at the same time, how they are also connected to the right block, where those are the HCAs, the network. So everything is quite balanced. The ratio is 1-to-1 for, I think, everything, which hopefully also means that it's a little bit easier to program. Now, if you compare this with similar systems of this category or of this size, this is EUM'25 Booster, the system that we have now, where you have the GPUs in the middle, the CPUs on the left-hand side, and then the HCAs and a PCI, well, 2 actually, PCI Express switches. The ratios here are different. Then you have all the NUMA craziness coming from AMD. It makes it a little bit more complicated to program efficiently. If you don't care about efficiency, then you don't care about that. But if you want to squeeze it, then you need to care about these things. And if you start comparing this with other systems like Frontier, where you have the red part are the GPUs, and then you have a single CPU, and locality becomes kind of a nightmare. Then you have Aurora, which makes it even more interesting. You have 8 HCAs, and you have 6 GPUs, because for reasons I'm not sure. We believe for a little. Well, I believe, this is just me talking. It's not JSC public opinion, but my opinion is that a ratio of 1-to-1 makes things much easier to program and to squeeze performance out of it, without getting too crazy about locality and things like that. Right, and we don't have a graphic for El Capitan. El Capitan, I think it also looks quite nicely in terms of all right, good. Network. I already mentioned a couple of things. From nodes to switches is NDR200, so the same bandwidth we have now, sadly. Yeah, only it's not infinite. In between switches is all NDR, meaning 400. All the links are 400 gigabits per second. Well, mention Quantum 2, ConnectX 7. It's a Dragonfly Plus topology with 27 Dragonfly groups. And well, here just some numbers in terms of number of links, logical ports, endpoints, number of switches. There's almost 900 switches on this thing. It's going to be interesting to manage. As opposed to UBLs, we intend to have Sharp enabled from day one, meaning that especially for AI workloads that rely a lot on all reduce, they can just push that all reduce into the network and skip one hop of data moving in between scenes. This is how it looks like if you plot it. scary. The green dots are the booster nodes. The orange thing in the background, those are the NDR200 links. In the core, in the middle, you see the NDR 400 links, and you see all the bunch of switches in the middle. There's other colors, lots of other colors. Those are either storage or cluster or admin or gateway, some things like that. That is the overall vision of the different Dragonfly groups. As you see, the booster part dominates heavily the network of 2725 are for GPU nodes. Then there's one small one for admin nodes, storage, things like that, and future expansions, and the other one for the CPU-based part of the system. If you zoom in, inside each one of these groups is a full fat tree with 16 L2 switches, spine switches, 15 L1s or leaf, whatever you want to call them. Right, so that is for all the GPU cells, and this is for the CPU cell. This cell is a little bit different. It has 32 span switches. The bandwidth into the rest of the fabric is the same between all groups. They are, in the sense, they are all fully symmetrical. The number of links going, global links, is the same. Just how it's divided is slightly different. Right, and then this would be for the admin and storage area. This is an old picture, meaning the ratio is not 100% correct, and of course the distribution was never correct. That was just to give a feeling, an idea, but the real topology, so to say, from the leaf switches to the nodes, yeah, this is simply not correct. Never intended to be. All right, software. And what I mean by software here is mostly on the admin area, but you see also the EasyBuild logo there. Actually, I just remembered that Sebastian also has some slides, so I'm gonna hurry up even more. Right, so we rely on Exascale. That is the cluster management software from Evidem. A very big part of the system, of the software, comes from that. Then as part of the consortium, we had also Partech. They take care of almost first level support, so they integrated some things for easing their workflows and taking care of checking the health of the nodes, things like that, and enabling a couple of features relevant for MSA. And then XOps, that's our in-house developed management software. It's basically a set of Ansible roles for managing everything possible. So we try to rely on Exascale as much as we can, but it has a few holes that it's not covering, and we are covering that with XOps. Right. In terms of technologies, things like that, well, it's Red Hat, Ceph, Kubernetes, Ansible, EUM'25, Cloud Init, things like that. I'm just rushing a little bit to don't eat the time too much. Learn, GPFS already mentioned it. For MPI, we have Parastation and OpenMPI. More and more people are interested on in-house and OpenMPI for GPU workloads. For monitoring, that is integrated in Exascale, but they use internally or inside Exascale, they use mostly cloud-based solutions. They use Prometheus, they use Thanos, Grafana, all those things. All right, and networks as a kind of central database for everything. The less distant past. Right, so I'm just gonna skip quickly. I thought 1 hour was a long time, but it's not that much. So this is a small view of the data center, of the new data center. It has what we call one data hall, where we have all the storage infrastructure, the admin infrastructure, things like that. And then 7 different rooms. You can see them there in blue. Each IT room is a 2-unit container, so 2 containers without a wall in between. Each of these containers with 10 racks. So in total per room, 20 racks. Right, and on the upper part of the diagram in orange, you have the power stations, 15 of them, 2.5 megawatts each. When you see that, do you understand why the current data center could not keep up with that? I think there we have, 8 or 10 megawatts. Yeah, here it's quite a few more. This is a render, how it looks like. This is, you can actually see it from outside now. So we'll see it there on the tour in a little bit. New power lines. The campus didn't have enough connection, connection to the grid is strong enough for this. Blah blah blah. Jedi was the first or development vehicle for Jupiter, so users had access to it for almost a year already. It's a single rack, but software-wise, it's almost one-to-one to what we're going to have on Jupiter. So I think that's been quite helpful, and actually that'll help us already to, at least on the political scene, to make some splash. It made it to the #1 on the Green 500 list last year. There was quite a journey to get there. It's interesting that just a single rack made it so high on the rank, and it's not even a single rack because the submission we made was with the rack half populated. So it's just one half rack is made it to 189 on the top 500 list, which is, for this size, to me, looks interesting. Right, the present. This is a picture from last week of the MDC. This is a picture from yesterday. So you see, if you compare both, you see that it grew already quite a bit in just 4 days. So things are, as I was mentioning at the beginning, the project is in a very hot phase, and I think it can kill me. Right, this is a time lapse of what was the area there. It's 1.5 minutes, and for the sake of time, I'll just quickly go to the end. But if I scroll to 1 minute, you see that not a lot has happened. And on the last 15 seconds, things accelerate quite a bit. We are now at the 1:20, I think. And then it just goes one thing after the other. So I'll just let it play. Lots of training. Right, and it ends last week. We didn't render, or well, there's an automatic service that is rendering this, but it stopped rendering last week. I don't know why. Good, and this is how it looks like. Or how'd you get there from here? I think you kind of recognize the room, I good guess. So if you go downstairs and then you go out, you will eventually reach the MDC. There was when we were talking about organizing it here, there was the wish, can we see Jupiter? Yeah, it would be nice, but it's probably not the right time. You will see quickly why. It is basically over there is a construction site. It's half construction site, half data center. It's not a place where we can take you guys. Sorry for that, but hopefully the video is interesting enough. This is the backside, by the way, and this is where all the basically all the IT stuff is that room over there was the batteries for the data hall. So in case of power loss, all this survives. This is what we call Exastor, the disk-based storage cluster, or Ethernet switch, well, one of them, or admin racks. So from those 3 racks, we manage everything, or will manage everything. And then the video goes into one of these rooms. Not all of them, there's 7 of them, but it goes just the inside one. And you see how more or less how it looks like at the moment. So there's 20 of these racks. Some of them are already fully cabled, and at the moment we are basically waiting for the building to be ready to be powered on and start cooling. We don't have power there yet, so that makes things a little bit challenging, and that's it. And these guys were like, "What are you doing? It's just for TV or what?" So at that moment, when I stopped, they were asking like, "What is this about?" All right. So as a quick summary, hardware on site from IT, of the IT rooms, out of 8, we have 7. The 8th one is actually empty, so it's relevant. It's relevant for the building to consider it complete, but not for the system. The power substations, there are all of them there. The adiabatic towers, that's the cooling towers. There's 10 out of 14. The other 4 will come, I think, next week. Racks, we have 120 plus 1, so there's 120 over there. There's 1 from Jedi on our current data center that is going to be moved somewhere in the next weeks. InfiniBand cabling, that's about 100 kilometers that have been deployed. It's difficult to quantify, out of about 300 kilometers. The complete control plane is there. The complete Exa store is there. Exa Flash, the storage based on Flash is expected for April. And for the near future, we have this coming up. The schedule is very tight. We are very stressed, but it's still, we think it's still possible, but it's definitely a challenge. We are aware of that, but working to make it a reality. Yeah, and then, well, some slides on how to get access to it, and that's it. So that's all. I ate all the time. Sorry for that, Sebastian. Now it's your turn. Questions, I guess we can have them yeah. I mean, I'll be around, and there's the tour, so you can ask me on the tour as well. Passing is done. Sorry. Sorry.
Yeah, I will talk a little bit about the software stack that we are going to use on the Jupyter system. And with software stack, I mean the software stack that the users are going to use. So in the software core team, we are 7 people. We are responsible for the core installations. That means GCC core, the compilers like GCC, NVHPC, then the MPIs where we have OpenMPI and Parastation MPI, and the mass libraries where we use like Bliss and we're also responsible for reviewing and merging the PRs that we get into our repository. And the PRs come from the software group. We have about 25 contributors for the current stage, and we have about 60 people in our JC internal EasyBuild chat where people can ask questions. So some of them are just curious and want to ask about EasyBuild. Some of them are actually building software locally with user installations in their account. Try that each of the module has one representative person that takes care of the application, and we try to map that to actually a person. So for example, for GrowMax, we have one person that is using GrowMax also in his lab for the simulation, and he is really an expert in that, and he's also then. The 25 people, what they are doing is they write easy configs most of the time, sometimes also easy block. They test then the software with the user. And if there are questions that come to the user support, they try also to answer these questions. We have our own repository, and you see that on the right here, a picture. We mirror that to GitHub, so everything is available. We try to increase the overlap with upstream so that we can contribute more from the work that the community is doing and that we don't have to do the work twice. The reason why we have our own repository is that, well, we want to be able to make modifications. Yeah? We want to be able to do a few things differently, but at the same time, we also try to keep it close to upstream so that users that want to take something from upstream can then also use. The stage 2025 is based on the 2024A toolchain generation. We have a few custom toolchain. This is a GCC Core FlexiBlast. That is quite a long name. The reason here for GCC Core FlexiBlast is that we want to have one Python and one SciPy bundle that we can use for all the compilers. Yeah, so if you load Python or if you load SciPy, you can use that if you use GCC or if you use NVHPC or if you use intercompiler. The other custom toolchains are GPS FBF. G is here, it's GCC. PS is then Parastation MPI. Parastation MPI is the one that we are here using next to OpenMPI, so we have a toolchain for that. Then a similar toolchain, but with the Intel compiler, so IPSFBF, and then two toolchains with the NVHPC compiler, one with Parastation MPI and one with OpenMPI. We have a few custom easy blocks, about 20, but we tried to merge most of these easy blocks to upstream. We have them in our repository. Sometimes they are not merged into an EasyBuild release, so that's why they then also are in our repository. But then once the new release is out, we remove them. We have a hook, and we make use of it for a few different things. So, for example, we ingest the contact information in the module information, and sometimes, so we have a few special modules, for example, OpenGL, which was presented earlier, and when a user is trying to take easy config upstream, we have a check in there that then replaces, for example, Mesar with our OpenGL. And then the last thing that is special, that is the naming scheme. So we are using a hierarchical module naming scheme. And I have here a picture how it looks like. So what we try to achieve here with our module UI is that we have an overview which is as clean as possible and as simple to understand for the users. So if you just log in and you don't have any modules loaded, this is what you see. I've shortened, of course, the core packages because not big enough. But yeah, you basically see only the compilers and the stages, and then the module for user installations. This is if someone wants to use EasyBuild to install something in the project space. You see that we have the production stages here. We have 3 different stages that are listed as production stages, and we try to support these or 3 stages all the time. What does it mean? So that means if there is some bug, we try to fix that. The older stages, so once we go on and add another stage, the oldest one is moving out of the list of production stages. We do not delete them, they're still available, but so can load them, but we do not guarantee that they are still working. So here we have 2025, the stage loaded. So you see that then in the compilers we have only one GCC, one Intel, and then NVHPC, you see, that's strange. You have 2 versions. Yeah, usually we try to have only one compiler in the stage to keep it simple for the users. With NVHPC, it's a bit special because that one has sometimes bugs, and the users run into that sometimes. So there is the need to have sometimes newer compilers to be able to, that the users can run their stuff. So, once you then try or load a compiler, so for example here GCC, you then see more modules. Yeah, so if you then type module avail, you see the different MPI runtimes and then also packages that are installed for the GCC compiler. Then, if you would go on, load the MPI, you would also see the modules that are available with MPI. Combination of compiler and MPI. This is the overview how it looks, and I have also a few number, how many packages we have here. So this is the stage view. We have one GCC core, then we have GCC, then the two MPIs for each compiler, and then we use FlexiBLAS on our. The building has been improved lately, so we now use Jacamar CI to help us and to support the installation on all the systems. We use a CI to check the easy configs, so verifying correctness and style issues. But then we also build and install the packages with the CI on the different systems. You see that we have quite a few systems, so we have I think 6 systems, and if you would have to log into 6 different systems and then type the same EB, this file command, this becomes a bit repetitive, so that's why we use here the help of the CI. And so let's assume the check is successful, then we first update here the repository on the HPC system. The fetch step, because we have a shared file system across all systems, we only need to fetch the sources once, because then they're available on all systems. So this one here is a serial step, but then it goes on, and this one is built then here on all the systems. So you see Eureka, Yusuf, Jules, and Jules Booster. So this is actually a very nice addition, and it helps us to save a lot of time. Then of course the question is, what about EasyBuild at JSC? And we are very, very happy that we have already EasyBuild available on Yusuf since a few weeks. Another thing is that the EasyBuild team got access to NVIDIA Grasshopper nodes here at JSC, be able to build also for the Grasshopper. And our plan is to bring EasyBuild also to Jupyter. Most difficult question at the moment is how do we handle the caching at the client level, because the nodes are diskless, right? So there we have to think about how we want to do that. Then the plan is that EasyBuild will in the beginning live next to our software stack, so that you have both. You can either load our stack or the one from EasyBuild. And depending on how that might work out, we could eventually at some point switch completely to EasyBuild and then build the custom packages that we need in with EasyExtend.
Okay. Thank you, Sebastian. Any burning questions? I think both Sebastian and Damian will be around on the tour as well. Anything urgent? So maybe on your very first slide, you showed how big the team is in terms of working with EasyBuild and the core team. And we had some discussions on this already, and also with Jens Hendrik. I talked a little bit about upstreaming things a bit more, like how can that be facilitated? What do we need to do? Or what can EasyBuild do to make that easier for Jülich? So that's probably a discussion we should have after this as well. But if there's any ideas there or any comments on that.
Yeah, so we try to encourage people to also upstream their easy configs that they're writing on. I would say out of these 25 people that are working on our repository, about 5 are contributing to upstream. That number has grown over the last 2-3 years, which is already good, but still there is room for improvement. And yeah, we need to figure out how we can increase that. So
maybe at some point, I mean, not right now because Jupyter is stealing all the time, but maybe at some point, like a dedicated workshop really focused on contributing back from Jülich to EasyBuild could make sense. Yeah.
Kenneth, I think one thing is that what we do a lot here is to move things from FOSS to GCC Core. Yeah, to GCC Core FlexiBlast in this case. That's because a lot of things that don't need MPI, we demote them to GCC Core FlexiBlast.
Yep.
And maybe having that on EasyBuild for everybody, because then it keeps you free from the MPI version, would be beneficial for everyone.
We've done some of that definitely over the last couple of years, but maybe not aggressively enough. Yeah. So, and that kind of input is very valuable as well. Maybe it's not directly contributing easy configs, but saying we need to change this because of this reason, and maybe this can just be pushed. And Jens Hendrik's work on OpenGL definitely falls into that as well. Yeah. Danger? What danger?
If you put FlexiBlast TC core level, you may end up with an Intel compiled module using the FlexiBlast compiled with TC core.
Yeah. Yeah, the thing you talked about in your talk.
The complex return functions.
Yeah.
But I think it may work if the FlexiBlast also loaded at the Intel compiler level. If that one takes precedence, then the FlexiBlast from Intel will be loaded. You just have to be really careful with mixing. If the same program uses a library that uses TC Core FlexiBlast, then you may end up pulling the linked FlexiBlast from TC Core FlexiBlast into the program that's compiled with Intel.
Yeah.
No conflict there. So that's what I'm saying. I've burnt my fingers before with TC Core and Intel combined, and I'd like say a warned person counts for two in the Dutch expression.
Okay, can we take this offline because we're 20 minutes behind schedule and we do want to do the tour thing.
We also started thinking about getting rid of C++ and Fortran from the GCC core.
Yes, yeah, that's another thing.
Also
But EasyBuild'5 will help with that. Yeah. There's features for that. Okay, thanks again, Sebastian and Damian. Yeah, we'll set up the streaming first before Burn kicks off. So we thought about sort of, I don't want to say funny talk, but a bit of a special talk to wrap up the meeting with. So Alan's going to set up the stream.